What did I say about the new conversations? And hold your questions till later. That counts as a question. Okay. We today did lesson 6, equivalent equations. So we are investigating what makes two equations equivalent. What are some ways that, stop talking, or I'll assign you more work. Since you guys want to keep using up my time, I'll use up your time. What are some of the ways we learned in the lesson that we can tell if two equations are equivalent? Like the solution, the value for the variable. So if they have the same solution, just because something has an equal sign, and something else has an. Okay. So if they have the same solution, then they are equivalent. How else can you tell? Same input and at the same time the output. Okay, same input, output. So yeah, if I plug in the same number into two different expressions and I keep getting the same answer, then yes, they are also equivalent. It really might look very different. What else? There's one that we did a lot today in my class at least. The other way that we know that two equations are equivalent, if we can link. So people that went through the lesson today, not necessarily just my students, but there was something you should have learned about the Tyler example. Or like the 2m minus 2i equals 10. So this is the, okay, stop. It actually wasn't written on the paper at all, but it. What? The first question. Okay, so for family B, we made a whole bunch of different equations that were all equivalent. Yeah. And then we kept making more, but we just had such a long list. So something is equivalent if you can do blank. Not just if they have the same variable, there's things you could add to this list that are wrong. Like if I were to do 5 minus m equals y, they have the same variables, but this would be wrong. Wouldn't be the same answers. What about all this stuff that we did on this side? All this scratch word. And it brought us to the Tyler example. Where if you can do blank, then there's a word. Okay, so we're getting closer. So maybe not the exact words I want, but stop guessing. I don't like your guesses. You didn't even have the lesson yet. And it's not even like in the realm of what we are talking about. Okay. So back to what Lila said, like if you do it on both sides, we're almost there entirely. But next one is like I'm literally about to tell you. Wait, don't tell me about it. No, don't. I didn't see it. No. Yes. Yes. How many times? So Lila was saying if you can do something to one side, you have to do it to the other. So if you can manipulate an equation to get the other, then they are equivalent. That was actually the main thing we did today. I expected that actually to be some of the first things you guys said. So they're equivalent and they have the same solution, the same input-output pairs, and if you can manipulate one to get the other. I will say. But here's your little list of all the different ways you can tell if they're equivalent. If you can manipulate one to get the other, then they are equivalent. And that could be, like for this example, that could be adding something on both sides to now get a different variable isolated. That could be subtracting something on both sides to get a new variable isolated. That can be multiplying on both sides. So really almost anything. You can even probably even do multiple things. But if you can manipulate it to get the other equation, then they're equivalent. So they would still have the same answers. So like in this random example where we were talking about how the difference between the middle and the youngest child's age is 5. So like if a random age, let's say the middle child is 8 and the youngest child was 3. If I were to plug that into here, 8 minus 3 is 5, right? 8 minus 3. 5. Okay, so that makes this one true, the one that's in blue. When I plug it into this, which is shown here, it makes this one true. 2 times 8 is 16. Negative 2 times 3 is negative 6. 16 minus 6 is 10. It makes something that's true, but it has the same solution. If you just multiply on each side, divide on each side, whatever the case, these are all examples of things that can be manipulated to each other. So when you do your practice and you see, hey, they look wildly different, they still could be equivalent. You just have to kind of like look at it and test it out. So like, for example, these two, like the second one and the fourth one, look the most similar. They don't look entirely similar, but they look the most similar. What's one way that I could go from 9 to 1? Good. But that's not what they did over here because then it would say like 8 minus 8, right? So try something else. How else can you go from 9 to 1? No, that would make it 27. What? We already canceled out subtraction. What did you say? You guys are bugging me with you guys not keeping up. We're comparing these two, the second and the fourth. Okay, I'm not really asking you much. I'm asking you how we can go from 9 to 1. We already ruled out subtracting 8 because if I was subtracting 8 over here on both sides, it would say a minus 8, right? And it doesn't. So how else can I go from 9 to 1? Divide by 9. That's why I wrote it here. Divide by 9 on each side would make the right side 1. And 3/9 is equivalent to 1/3. So I can manipulate this one to get that one. Even though that's not a step in solving, like these other ones, like this is a step in solving this. These other ones can be manipulated to get these. So like this one over here looks most similar to this one. What could I do to go from 15 to 5? By what? 3. Yeah, you could divide by 3. 15 divided by 3 is 5. See if that's what happened with the rest. What's 3a divided by 3? 1. 1a. So the A is still there. What's 6 divided by 3? So you can manipulate this one to get that one. And vice versa. Like you can multiply 3 on each side to get this one. So just because they look wildly different, try to see if you can like add, subtract, multiply, divide something on each side to make them now equal. Like to better see that they are. Or you can solve each of them, but that's up to you. That might take longer. But yeah, they have the same solution. They're also equivalent. Questions on that? Okay. So even though some of you haven't had the lesson, I would say that the practice is hard without having had the lesson, but we just went over the learning targets. I think you should have enough to be able to do it. So 80% or higher is the standard. I'll leave this list up here. So lesson 6, number 1, that one, we have which equation is equivalent to 6x plus 9 equals 12. We have a few ways, and later on I'll even show you another way that's even like easier. But with what we learned today, I'll go based off of that. If you can manipulate one to get the other, then they are equivalent. So like just comparing x plus 9 equals 6, you could ask yourself, like kind of just like pick a part to focus on. Like how can I go from 12 to 6? Good, you could subtract 6. That's not what they did on this side though, because then it would be like 6x plus 3, right? So how else can I go from 12 to 6? Okay, good. And then I also know that's not what they did because then this would be like 1/2 x and this would be 4.5, which the 9 didn't even like change. So I know it's not that answer. So now look at the next one. And by the way, these are like almost all in the same setup. It's always like the x term, the number without the x, and then equals a number. So that's how I can like easily compare them. For this one here, the second one on my screen, how can I go from 12 to 4? Okay, so I'm going to see if I divide each term by 3, if I get that answer. So sorry, just waiting for my pen to load. Okay. Because it's a rule like whatever you do to one side, good, and you'd have to do it to this entire side, which is the same as doing it from each of these terms, so I'll have to do it from each. What's 6x divided by 3? Good, 2x. And then what's 9 divided by 3? And 12 divided by 3. So because I did something on both sides and I got this equation, that's the one that's going to be equivalent. The rest, like this one, you could say dividing 2 on each side, but the 9 wasn't divided by 2, like the 9 didn't change, so that one can't be equivalent. This one, you could say like I mean, this one just kind of just doesn't really make sense. Like you could try subtracting 3 on this side, but then 9 minus 3 is 6, so like this would have had to been 6. So that's the only one. So that's one way. If you can manipulate one to get the other, then it's equivalent. The other way could be to like solve each one, but then that's kind of tedious too, but it would work. It would give you that, let's see, I subtract 9 on each side. It gives you that x is 1/2. So then like 2 times 1/2 is 1, 1 plus 3 is 4. Like it would make that true also. But then if we go back to like our little list, let me see if it's still here. Okay, no, I guess I got rid of it. The other way was to see like if they had the same table of values, which we know like if we graph table of values, like they should be in the same spots. So the other way that I didn't tell you guys today, because then it would have just been like you wouldn't have tried any of the other ways, is if I graph it
and it makes the same line. So like 6x plus 9 equals 12, 2x plus 3 equals 4. It makes the same line, like they cover each other, then that's another way you know it's equivalent. So if I change this to like one of the other answers, like the x plus 9 equals 6, that's not equivalent because I can still see the red line, like it doesn't cover it. Does that make sense?
Yeah.
Okay. Any other questions, anyone?